Yeah. Okay, so first speaker is Shuwa Miura. Something like this, talking about automatic extraction of axioms for planning.
Okay. Thanks for the introduction. My name is Shuwa, and this talk is on our paper, Automatic Extraction of Axioms for Planning. So let me first introduce a single agent puzzle game, Sokoban, which is used for illustration throughout the presentation. So in this game, as you can see, the player pushes stones around in the maze, and the goal is to push all the stones to their destinations, which are indicated by the red marks. And Sokoban can be formulated as a planning task using sus+ formalism, where each state is characterized with multi-valued variables. Sokoban has mainly 3 variables, and a clear variable describes whether a location is clear or not. And at player and at stone variables describe stone's locations and player's location respectively. And we have 2 operators in this task. A move operator moves a player, while a push operator pushes a stone. And that's how Sokoban is usually formulated. There is, however, another formulation of Sokoban using logic program-like rules called axioms. And axioms are rules for determining the values of secondary or derived predicates from the values of more basic predicates. So here, axioms determine the values of reachable variables, which represent whether a particular location is reachable from the current player or not. Intuitively, the first axiom states that the current position of the player is reachable, which is sort of obvious. And the second one states that the adjacent location to the reachable locations are also reachable. So in this example, the player is in the position 6-3. Since this satisfies the right hand of the first axiom, we can conclude that 6-3 is reachable. And if you look at the second axiom, since now we know 6-3 is reachable, the second rule fires. And we can conclude that the adjacent locations are also reachable. And just like that, we can keep firing axioms to determine which location is reachable for the current position of the player. In the formulation without axioms, we have 2 kinds of operators: move for moving the player, push for pushing a stone. But now that we know which location is reachable from the current position of the player using axioms, we can actually remove push operators entirely. And push operators in the new formulation have reachable as the precondition instead of at player. The resulting player's behavior is animated in the slide, and note that the player kind of teleports around in the maze to push stones. Right? So comparing Sokoban modeled with and without axioms, we can see that modeling with axioms leads to smaller search space and shorter plans. And this is because the formulation with axioms leaves out irrelevant choice of the exact path the player takes to get behind the stones, right? But it's not really obvious for domain designer that Sokoban can be formulated compactly with axioms. So we propose a novel method for automatically extracting a particular class of axioms given a problem originally formulated without axioms. So that's our motivation. So the overview of our system would look like this. Since many of the planning tasks are written in PDDL, we first translate or ground the problems into sus+, and we then look at grounded problems and see if there are any unnecessary operators, such as move operators in Sokoban. And as I'll explain later, we also do some analysis to identify inessential variables. The next step is to express the identified unnecessary operators and variables as axioms and get the equivalent problem as the original problem. Then the encoded problem can be fed into any domain-independent planner capable of handling axioms. And a solution to the encoded problem with Axioms is a partial plan to the original problem, since we might be missing some operators expressed as axioms. So in case of Sokoban, a partial plan consists only of push operators. So to obtain a complete plan for the original problem, we need to restore a complete plan from a partial plan. So in case of Sokoban, we fill the gaps between push operators with corresponding move operators. So our main contributions are new methods for extracting two types of axioms. And one is called tau axioms, which represent unnecessary operators. The other one is called epsilon axioms, which represent inessential variables. And we showed these axioms can be extracted from many IPC domains. And we also used extracted axioms to speed up integer programming-based and answer set programming-based planners. Okay, let me first explain tau axioms in more detail. So the key observation why move operators in Sokoban can be axioms is that move operators' effects become irrelevant given a push operator. For example, the player could follow the blue arrows to get behind the stone, but he could also follow the red arrows to get behind the stone. And the important point is that the path taken to get behind the stone does not really matter once the player pushes the stone. So we only need to keep track of reachability from the current position of the player. And we call operators like move whose effects become irrelevant given some other operator. And tau operators can be transformed to tau axioms. In this case, move operators can be transformed into reachability axioms I described earlier. And we identify tau operators using the notion of dominance between two operators. An operator O dominates another operator O dash if and only if variables in O dash effects also appear in the precondition of O. So in case of Sokoban, since at player variable in effects of move also appear in precondition of push, by definition push dominates move and the effects of move become irrelevant given a push operator. So that's the main idea. And we want to partition the set of operators such that every operator in one partition dominates every operator in the other partition. And we propose two algorithms to do that, but I only have enough time to introduce one of them. So in graph-based tau axiom extraction, we consider a directed graph consisting of grounded operators. And there's an edge between two vertices if and only if there's a dominance relationship between the corresponding operators. So we consider the complement graph of the original graph, and we run strongly connected component algorithm on the complement graph. And if we pick any of a sync strongly connected component with no outgoing edges to the other component, then in the original graph, there's an edge from every vertex in the component to every vertex in the other component. So we found tau operators. So that's how we extracted tau operators. Okay, so far we've looked at tau axioms that represent unnecessary operators as axioms. Now we look at epsilon axioms that represent inessential variables. So remember that in Sokoban we had three kinds of variables. However, if you think about it, the values of clear variables can be completely determined by the values of other variables. And the epsilon axiom captures this relationship. And the epsilon axiom means that if there's no stone or player in occupying a location, then the location is clear. We use the idea of exactly one invariant to derive epsilon axioms. A set of fluents G is an exactly one invariant if and only if exactly one member of G is true in every reachable state. Exactly one invariant has been used in planning for many years. So for example, every sus plus variable is an exactly one invariant. That player variable captures the fact that the player can only be at one location, and likewise that a stone can only be at one location at the same time, and the location can be clear or not. But there can be exactly one invariant that are not captured by sus plus variable. So for example, in Sokoban, each location can be occupied by at most one thing, so there cannot be a stone and player occupying the same location. And the idea is to turn exactly one invariants to epsilon axioms. So if you look at the clear variable in the exactly one invariant, when all the other variables are false, the clear variable must be true because this is an exactly one invariant. So we find exactly one invariants using existing techniques and turn them into axioms, which we call epsilon axioms. Okay, now moving on to the experimental evaluations. We tried tau axiom and epsilon axiom extraction on 44 domains from IPC, excluding domains with complex features such as conditional effects. And here's the list of domains where axioms were found in at least one of the instances. So for example, in blocks world, whether a block is clear or not was identified as epsilon axioms, and in Myconic, the up and down of the elevator was identified as tau axiom. Okay, so although the algorithm to extract axioms from planning instances are our main contributions, we also evaluated this overall system using extracted axioms. And for domain-independent planner, in the search component, we used model-based planners, hoping that they exploit shorter plan lengths of reformulated problems. And by model-based planners, we mean planners that translate planning instances to other formalisms such as SAT, right? However, since existing model-based planners don't handle axioms, we had to develop axiom-aware planners, IPlan and ASPlan. IPlan is based on integer programming, ASPlan is based on other set programming, and the details of those planners are in our workshop paper. So please refer to the paper for the detail. So in the experiment, we used all 22 IPC domains where axioms were found, and as you can see, configuration with the extracted axioms improved the performance, and this is the result for IPlan, and we got the similar results for ASPlan as well. And this is because extracting axioms resulted in shorter make spans or plan lengths. And so the plot compares make spans between configurations with and without axioms. Okay. We also did some evaluations with state space search planners. In these planners, extracting axioms resulted in less expanded states, but not in speedup because of the overhead in evaluating axioms in each state. So, in summary, we proposed two types of axioms from PDDL domains. One is tau axioms, which represent unnecessary operators. The other is epsilon axioms, which represent inessential variables. And we found axioms in many standard PDDL domains. And we also showed that we can speed up model-based planners using extracted axioms. And that's all. Thanks for listening.
Question?
So fast downward does pre-processing to turn representation.
Yes.
And in doing that, it's finding invariants
Yes.
that essentially amount to the epsilon axioms that you're doing, I think.
Yes, so we rely on fast downward to find these exactly one invariants, but our contribution is that we express them as axioms to show.
The question is, after it has done the translation, right, are you still finding additional epsilon axioms after it's done that translation? Because if you were applying fast downward here, you seem to imply that you're getting smaller space because of those epsilon axioms, which means you're finding something that it's not.
So the reason why we get smaller such space is actually due to tau axioms, which represent unnecessary operators, because epsilon axiom just capture the relationship among variables, and which variable is like most essential to the domain or not. So if that makes sense.
Right. Well, if it found, when it finds an invariant, right, it's going to turn that into a single variable.
So we are doing our analysis.
Yes, it does.
So we are doing our analysis after using fast downward translator. So we are working on sus plus grounded formulations.
So nice work, by the way. There are methods to compile away axioms into axioms. Did you try to, do experiments where you were compiling away axioms and see what your method could recover and how similar it looked like to the original?
We did, and there's some limitation on our on our current work. So we rely on variable to identify unnecessary operators, and we couldn't compile back to the original problems with, say, so we couldn't compile back to the original problems. Yeah.
Actually, I have probably a quick question as well. Since, as you said, it's only the tau axioms that reduce the search space. So what is the benefit of the epsilon axioms? What are they good for?
So, well, firstly, it gives you some kind of intuition which variables are most essential, and we haven't looked into it, but you could probably use some abstraction heuristic, and also in domains such as blocks world, extracting epsilon axioms actually improved the performance, but it's probably due to the underlying integer programming solver, and we haven't really looked into it yet. So,
all right, we'll stop there if we have time. Oh well, yeah, okay, fine.
So you said you looked at cases where you found axioms for at least one instance of the domain.
Yes.
So were there cases where you found axioms in some instances but not the others?
Yes. So there are some kind of accidental axioms. So in some domains where you have several tracks, in instances with only one track, we managed to find axioms. But in instances with multiple tracks, there were no unnecessary operators in these in problems.
Right. I'm trying to speak.
Yeah, thank you.